This is Embedded System Design class, and today we will talk about Lecture 2, which is basically an introduction to our choice of microcontroller, which is PIC24. So we said last time that there is a difference between microcontroller and microprocessors. So know that the division between microprocessor and microcontroller, they are actually becoming increasingly blurred. So it's kind of not difficult, but not easy to differentiate between a microcontroller and microprocessors. As we said, just to give you more hints, a microcontroller is a single chip solution, while a microprocessor requires external support chips like the memory and IOs and many other interfaces. The microprocessor has more interface functions on chip, like serial interfaces, meaning communication modules, and analog to digital conversion, timers, etc. While the microprocessor is just a bare CPU. The microcontroller usually does not have virtual memory support, while the microprocessor have virtual memory support. At this point, actually, newer version of microcontrollers, they can actually run lightweight operating system, for example, Linux. And microcontroller, a low performance specification, like the clock speed, the data width, an instruction set, and the cache, is actually goes along with the requirement that to make microcontrollers cheap. So that's why we have low performance specification. While the microprocessor or the microprocessors have high performance specifications in all of them, and this is why it's expensive compared to the microcontroller. And that's actually what we mentioned in the last point. Now, since we choose PIC24, we need to read the PIC24 data sheet. If you go to any PIC24, whatever your choice is, you will have a data sheet around 200 to 300 pages describing every aspect of that microcontroller. Usually it's broken into chapters. One chapter will describe the PIC24 microprocessor, the CPU, the register file, the program memory, and the data memory, and more than that actually is described there. Also, every single module of the microcontroller functionality is also discussed, such as the input-output ports. We have in PIC24 two ports, port A and port B. The oscillator, the timer, the SPI, the USART, and the other modules. They are described in detail in its data sheet. However, the gist of these modules, along with the CPU, we will discuss them thoroughly in this talk and the next videos. So we chose of PIC24 this family, which is PIC24 Ch3 GP202. Also the other variant where you have 128 instead of the 32. If you go to the data sheet in page 3, you will see many of the essential features of this PIC24. You can see that the data path width or the microcontroller type is 16 bits. This is why we consider the type of this PIC24 a 16-bit microcontroller type. The instruction width is 24, and that's why we have 24 here in the name. The on-chip program memory, the non-volatile one, it's also electrically erasable. Its architecture supports 4 million instruction, or 2 to the power of 22. It's 32 kilobyte, and the user program can have up to 11,264 instructions. We will see how these numbers are shown in the program memory itself in the next few slides. On the on-chip random access memory, the PIC24 have an architecture that supports up to 2 to the power of 16, which is 56,536 bytes, or 2K with 2K bytes SRAM. Also, we will see how is this broken down when we talk about the data memory. The clock speed, it has a maximum of 80 megahertz. You might think that this is kind of low if you compare it to the frequency of modern processors. However, remember that this microcontroller will be part of the embedded system that is hidden inside a bigger system. So usually we don't have, or we don't need very high frequency, for example, for a remote, or a remote that's controlling a TV, or for a system that's basically part of a toy. This is why we don't really need high frequencies. The architecture is actually general purpose. It has general purpose registers with 71 instructions, not including the addressing mode variants. And you can see detail of the ISA, or the instruction set architecture, in the data sheet in one of the appendix. The on-chip modules, there's so many. We have the GPIO, we have the I2C, we have the SPI, the analog digital converter. We have also 3 16-bit timers, and we have 1 8-bit timer. Also, we have a converter. So, if you look at the CPU, this is a very simplified version of the CPU of PIC24. You can see that you have a program counter that gives you the address of the instruction that you can, or actually with this address, you can address or you can access the program memory to get the instruction that you want to execute. Currently, you have up to 4 million words, which is basically 4 million times 24, because every instruction in the PIC24 have 24-bit width. Once you get the instruction that you want to execute, you store it in the instruction register, and you can either access the register array or the register file, or access the data memory based on the instruction, and you can get the data required for the execution in the CPU or the ALU. And once you get the results based on the instruction type, whether it's having an operation that you need to execute, or you need to access a certain data in the memory, whatever is the instruction, you get the result, and now you can feed it back to the ALU, or go access the memory, or go access again the working register array to do the appropriate calculation. So as you can see here, some of the things that we need to be or we need to point out is the width of the instruction. Every instruction width is 24-bit, and this is why we have PIC24. You can see that this is 24. However, the address, we need only 23 bits, and we will describe this soon, why we only need 23 bits. Also, the width of the data buses here, you can see that the width everywhere is 16 bits, and this is why the type of PIC24 microcontroller is 16-bit microcontroller. We have also the instruction registers that contains the machine code, as we explained, and the ALU, or the arithmetic logic unit, is actually 16-bit. You can see the input have 16-bit and the output also 16-bit. And it accepts operands either from the working registers. We have specific names for these working registers, W0, W1, all the way to W31. And or you can get it, if you get it from the working register, they will be in this array here, or from the data memory, as you can see here. Now, just to remind you about the architecture class, we said that in the architecture class, we have certain registers for the MIPS ISA, and those registers could be S registers or T registers for temporary, and so on. The naming of the registers in the MIPS is different than this microcontroller. Here we call them W registers, from W0 to W31. Now, after this brief discussion of the CPU, let's go to the memory organization. We have a split memories. We have program memory and data memory. In the program memory, it's non-volatiles. Also, the big instruction is 24 bits or 3 bytes. And this microcontroller supports 11,264 instruction that you can put in the program memory. The PIC24 architecture can support up to 4 million different instructions. We will see why soon. The PIC24 data is stored in data memory. That's the difference between the program memory and the data memory. The program memory stores the code. The data memory stores the data or the variables. They are also known as a file register. Its maximum size is 56,536 times 8-bit. The data memory, as you know, is volatile, meaning that the contents are lost when the power is off. Now, let's talk more about the program memory. If you address the program memory, as you can see here, from bit here, starting from bit 0 all the way to bit 31, you can see that there are 3 bytes here, and we have one additional byte, what we will call a phantom byte. The reason we add this phantom byte to work with a power of 2 width, which is 32 in this case, it's much easier. And because of this phantom byte that we added, now we can address every instruction by even addresses, starting from 0 and then 2 in hexadecimal, 4 in hexadecimal, and 6 in hexadecimal, and so on. You can see that there is also this address, which is the odd address, 1, 3, 5, and 7, but this will address half of the instruction, which is meaningless. What you want is the whole instruction. So you start with this address, and it will give you the whole 23 bits along with the phantom byte. Now, as we mentioned, that the program counter is 23 bits wide. As you can see here, since we are having an even addresses, the least significant bit of all of them is always 0. This is why we don't need 24 bits to distinguish for each one of them. we can have only 23 bits address, and you can access the instruction that you like. The instruction starts on even words boundary, as we said. So the BC least significant bits is always 0. You can have a simple practice here, just denoting or representing the decimal number from 0 to 9. So if the decimal 0, 1, 2, 3, 4, 5, 6, 7, and 8, and you have 9 here, you can see that. Let's write the even addresses here. We denote them with E, and the odd addresses here, and we denote it with O. So this will be 0, 0, 0, 0. This is 1, 0, 0, 0. This is 2. This is 3, which is 1, 1, 0, 0. And this is 4, 0, 0, 1, 0. This is 5, 1, 0, 1, 0. This is 6, 0, 1, 1, 0. This is 7, 1, 1, 1, 0. This is 8, which is 0, 0, 0, 1. And the last one is 1. And you have 1, 0, 0, and 1. You can see that the even numbers, they all start with 0. You can see that the bit in the least significant bit position is always 0. While the other one you have 1 all over the odd numbers. And that's why, since we know it's always 0, there is no need to feed it from the PC. We can have only 23 bits. Now, we said in the program memory, and this is detailed in this page and PIC24 data sheet, that the architecture supports 4 million instruction. And the reason is, if you go there and you check the program memory, you can see that it starts from 0x000000 in hexadecimal all the way to 0xFFFFFF. The reason it's E here because we have the width 16-bit. So the first half byte is with address E, and the last half byte with address starting with F. The point here is that we have 6 hexadecimal digits, meaning that we have 24 bits. And as we said, we will consider each instruction is 3 bytes plus 1 phantom byte. The total is 4-byte instruction. Now we divide 22 to the power of 24 divided by 1 instruction, so to see how many instructions we have. And by calculating this, 2 to the power of 24 divided by 2 to the power of 2 equals to 2 to the power of 22, which is equal to 4 million instructions. So that's what the architecture support. If you fill it with all instructions, the whole thing, you can have up to 4 million instructions. But that's the possibility of the support. You can see that we break it down in many regions. Some of these regions are reserved and we are not going to use it. Some of them are used for other things. So starting from the beginning, you would see that we have go-to instructions. Basically, this go instruction helps you to identify the starting of the code. In C or Java, we call it the starting of the main method. Also, we have the reset address. This is supposed to be reset address, and the vector tables. You can see this is the goto, this is the reset, and we have a vector table for the interrupts. As we mentioned before, if you have different interrupts, each one of them have its own interrupt service routine. You need the beginning of each one of them, and you list them in this vector table. Also, you can see that you have an interrupt vector table and you have alternate vector table, which is actually a copy of the vector table for reliability and dependability reasons. This is from location 0x000000 all the way to FF1000 in hexadecimal, basically this region from here all the way to here. You can't add your code here because it's already reserved for other needs, as you can see. So now, if you have a code, you can put your program or you put your code in the program memory, starting from this location, which is 002,000, which is this location right there. You can start writing your program. The first instruction or the machine code of your code will be here, following by the next one, all the way. As you can see in this location, starting from 002 to this place here, has the capability to store 11,264 different instructions. So this is the maximum size of all the codes that you can put in the program memory of this microcontroller. This means that later when we introduce the modules and we wanted to have a specific functionality that runs in the microcontroller, your code should be as short as possible. And you will see with the coming of lectures that all the codes that we are using is fairly short. The line of codes are very small compared to what you are used to have in other courses. So that's what you need to remember, that the starting location is 0x002 or 200 in hexadecimal. You can look at the other things. Here, you know that this region is unimplemented. This is reserved, and this is for the device configuration registers. This is also reserved, and this is for the ID. Now, you could say that why we have all this space reserved? I could have used it for my code. The reason is basically this is a micro chip company architecture. They have many families, they have many microcontrollers, and they want to align them together as required. So sometimes they are forced to have a region reserved or unimplemented, so they align easily with other versions or other similar microcontroller from the same family. Now moving along to the data memory organization. This is on page 24 of the data sheet. We said that the architecture supports 64 kilobyte. Again, here we have now 4 hexadecimal digits, meaning that we have, this means that we have 16 bits. So 2 to the power of 16 is equal to 64 kilobyte. And this figure, we have the width of the memory represented in 16-bit. Now we know that the memory is a byte, is organized byte-wise. So this is the first byte, it will be here. The second byte will be next to it, and the third will be here, the fourth will be here, and so on. As you can see in the data memory, we have 2 important sections that we need to highlight. The first section is the SFR space. The SFR space is for special function registers. So we have special registers for special purposes. We will talk about them more in the next slide, but this is their space. It starts from 0000 all the way to FF70. So they have this space. Right after that, we have the 2 kilobyte that we mentioned in the beginning of the lecture in the table, on the summarized table. So it has a 2 kilobyte RAM starting from location 0x008 all the way to 0x FFF and 0. Now, it's important to know that in data memory, what we are saving in this region is the variables. They are the variables that we have in our code. So if one of the instruction have two variables that you need to do some operation on them, the first and the second variable will be stored in this region. If you want to store them in the first location of the memory, it will be in location 0080, and the next one, if the variable is only 8-bit, will start in 108. And we will see this further in one of the simple programs that we will mention in this lecture, how the variable are organized in the RAM, and also the code segment that we said that it will start here at this location. Okay, we mentioned the special function register. The special function registers, they are addressed memory location that have specified functionality tied to hardware subsystem in the processor. Now, examples of the processor subsystems are the serial peripheral interface, the timer, the analog to digital converter, basically the modules that we talked about. We said that the microcontroller is the CPU plus other modules. These modules, each one of them has its own special function register that you need to set up to control them. Their special function register, the one that we just mentioned here, they are, for example, for the serial peripheral interface, is called the SPI1 control register number 1. And the analog to digital, for example, in the timer, you have timer 3 control register. We have timer 1 control register and timer 2 control register as well. We will talk about this when we talked about when we talk about the lecture about the timers. The analog to digital converter, for example, this is one of its special function register, AD1 control register number 1, respectively for each one of them. There are several other special function registers. I can't list all of them. There are a huge number of registers. If you go to the data sheet, you'll see long list of special function registers that are required to control any module in the microcontroller. Now, we have also the general purpose register, which is basically also an addressed memory location, but they are used now to store data variables that are allocated randomly in the region that we mentioned here. So this is basically the SFR, and here we have the GPR. Most of the registers in a typical RAM are GPRs, and GPR are called sometimes file registers. Now, just to make sure that you know the basics related to data, we can have 8-bit data or 16-bit data or 32-bit data in our microcontroller. So these are the data types that you can define in any code. So 8 bits is a single byte, 16 2 bytes, and 32 is 4 bytes. And you can see here that the 8 bits range from 0 to 2 to the power of 8 minus 1, from 0 to 255, or from 0 to 0xFF in hexadecimal. This is for the 16-bit. This is the range you can see. You can see that the maximum range is 56,536, which is all F. The 32-bit, we have up to more than 4 billion. Now, the lower 8 bits of the 16-bit value or the 32-bit value, we call them a special name, which is the least significant byte. The upper 8-bit, we call it the most significant byte. Remember, we have the least significant bit and the most significant bit. We also have a least significant byte and a most significant byte. Now, suppose you have this value that you want to store in the memory, which is 0x, and you can see that in hexadecimal, it's 0, 1, 2, 3, 4, 5, 6, and 7. How do you store it in the memory? There are two systems, either big Indian or little Indian. For the big Indian, if the locations that you are saving this value on, notice that this value is 32-bit. This is 32-bit. If we start from this location, 0x100, and then followed by 0x101, 102, and 103, if you adopt the big Indian method, what you will do, you will store this value first, this byte here, followed by the next byte here, followed by the next byte, followed by the next byte. This is what we call big Indian. We start from the most significant byte first. And the little Indian, we start from the least significant byte first. So you have 6 and 7 first here, and then followed by 4, 5, followed by 3 and 2, followed by 1 and 0. And we call this little Indian. There is no advantage of one of them over the other. You might think that this looks better, but because of this example, it shows that I can give you another example that makes the little Indian better than the big Indian. So there is no difference in which one to choose. But if you pick one, you are stuck with it for the whole time. And PIC24, we choose the little Indian order. So if you have 16-bit value or 32-bit value that are stored in the memory, we store them with little Indian order. Here are some examples here. Let's say that you have a 16-bit value, which is this one. This is 16-bit value. And you want to start saving at this location, which is this one. So in little order, you start with the least significant byte first. So you have this one first here, and then followed by this one. If you have another value, which is 32 bits in this example, then you will follow by AC, and then 25, and then 90, and you end up with F1. If you show your memory as 8-bit wide, you do it as we described. If you show your memory as 16-bit wide, then whatever value you have as 16-bit, you copy it here. And then now here you have the least significant 16-bit, which is this one, followed by the most significant 16 bits here. So basically what we are saying here is that PIC24 is adopting the little Indian order. Now let's have a simple program. I write this program in such a way that you make it or you can understand it if you study any programming language. But know that in this class, we will present our programs in C, which is a high-level language. And then you can use a tool to translate it or compile it into the PIC24 assembly language. The tool that we are going to use in our class is called MP Lab. This tool is, you can download it and install it for free from the Microchip website, and you can also install the MP Lab is actually an IDE. It's basically an editor, and you have to install the appropriate compiler for your microcontroller. The appropriate compiler for our our microcontroller is a 16-bit compiler, and the reason is because of the type of the compiler, as we specified earlier. Now, to simulate, when we say that you need to simulate the program, to simulate, this means to execute the program without actually loading the program into the PIC24 microcontroller or the real hardware. So for this program, it's fairly easy. We have this defined statement. We define a value to be 100. And then we define also some variables, I, j, and k, and we make them unsigned integer 8-bit variables. This is one of the types that we are going to use for the variables. You will notice, and we will mention this later, that we have a few types: unsigned integer 8. We have integer 8, or the signed version. We have unsigned integer 16, if you want to specify 16-bit. And we have the 32-bit, the unsigned version, and also the signed version. So you can specify them easily by the correct type. So now we know that I and j and k, they are 8 bits, and they are also unsigned values. 8 bits is obviously, as we mentioned, is 1 byte. So this is for 1 byte. This is for 2 bytes, and this is for 4 bytes. Now we say that I is equal a value, meaning that the I will be equal to 100. In the next statement, or C statement, I is equal I plus 1, which is basically incrementing the I. Now the value is 101. In the next statement, we have G equal to I. So, or sorry, J is equal to I. Now J is 101. The next one, J is equal to J minus 1. So basically we are decrementing the value of J. So now it's 100. K is the addition of both J and I. So you sum them up. So the result will be 201. You can see that these values are this code is very easy to understand. Now, the purpose of having this code is to see how the microcontroller generating the assembly language for it. So we use the MPLAB. We write it down here. Once we compile it, it will generate the PIC24 assembly language, or PIC24 instructions. So now, when writing the assembly language, you can use any free data memory location to store the values. But we know that for the data memory, the starting address where you can store the data is 0x0080. Because these locations from the beginning all the way to 0xFF7 is reserved for the special function register. So now, since we know this information, we can assign the value or the variable I to this location, which is the beginning, 0x008. J will be 0x108, and K is the following location, which is 0208. Remember, this is data memory. It could be random. It could be anywhere. But we chose that to make them sequential. Okay. So now what will happen? These very simple statements, after we compile them using the C compiler, we write them down in the MPLAB IDE, and then we compile them. They will generate this assembly instructions. Notice that all of these instructions has this extension .p, .b, indicating that all of these instructions are 8-bit instruction. 8-bit instruction. So here, this assignment, what we did here is we assigned the value of 100 to the working register number W0. And if you remember MIPS that you studied in the computer architecture, for example, if you have the add instruction of, let's say, T1, T2, and T3, those three temporary registers, what will happen is it will add those two variables together. So it will take this one and this one, add them together, and the result will be put in the first operand that you see after the opcode of the instruction, which is add. Here it's the other way around. And this micro, in our PIC24, is the other way around. So you assign in the operand in the last or away from the opcode of the instruction. So now we have W0 is equal to 100. Now also we need to move it to its location in the memory. And to move it in the memory, remember in the MIPS we have a load instruction or a store instruction if we access the memory. Here we use move, the move instruction. So you move the W register and you move it to this location. The assembler will know that I will take the value that is in the W register and I put it in the data memory at this address, which is 0x00 and 8. Notice that the W0 is actually the same, exactly the same as the W register. The W register is usually, or then another name for it, or the way we state it is the working register. Even those register, we are having working register number 0 and so. However, in this lecture, we will look at the assembly. But later, when we look at the modules, all our program will be in a high-level language, which will be in the C language. Okay, now we move to the next statement. The next statement, since it's only an increment, we have an instruction for it, increment 0x008. So it will go to this location and increment the value in that location. The next one, we have an assignment. The I goes to J. So you move the value from this location to the W register, and then you move the W register into the next location for the J, which is 0x1, 0, and 8. You can see that this is what's mentioned in the comments. And by the way, when you have a semicolon here after every statement, this is a comment. That's not going to be converted to machine code. The only thing that is converted is the instructions of the assembly code. Now, next, we have this value, which is a decrement of the value of J. This statement will be converted to this instruction, decrement 0x108. So the location in the memory 108, you go the value there and decrement it. And then after that, the last statement, and notice that this last statement is converted into 3 instructions. Other statements, it's only 2, as these 2. So we have 2 instructions here, we have 2 instructions here. Those 2 statements, or these 2 statements, have only 1 instruction. So it's a 1-to-1 mapping for the increment and the decrement. But the more complex the work, the more instruction you will have. So for this one, you will get the I first. So you will get the I to the working register. And then you want to get the J and add at the same time. And you have this instruction for it. You can have this instruction add. So you get the J from 0x108. You put it in the register, but you accumulate it with the previous value. So this way you add both I and J. And then after that, the last one, you just move the resulting value to its correct location, which is the K location, which is 0x to 0 and 8. Now we could perform this step, or if you want to move from assembly to machine code, you can do this manually, but it's going to be a little bit tedious. And this is why we choose, or we use, an assembler. Also, the MPLAB IDE, it has a compiler that compiled the C language to an assembly code. And also it has an assembler to have the, or convert the assembly code to a machine code. Next, we will see, or we will show the assembly of our simple C code as it is shown in the MPLAB. In the discussion that we just had, we take out most of the surrounding details. Now we will see exactly what happens in the MPLAB, and we will try to understand together what's going on in the code. So here we have this code. It's called mptest_byte .s, meaning that this is the assembly instructions. You can see that it starts with some of the headers, directives that start with dots, some spaces for the variables, and then it starts having the code. You have a label here, you have some statements, and then you have the statement that we just described here and here and here and here and here, and so on. These statements that we just described. But you have things that in the beginning, and also you have at the end some statements or some instructions. Again, just to remind you, I is in 0080, the J is in 108, and the K into 08. And this file can be assembled by the MPLAB assembler into the PIC24 machine code, and it could be simulated. So let's take every piece of code here to try to describe it. So in the beginning, you have this part here. So this part, what we have is the include, which is basically you include certain library that's already written. You include the file that defines various labels using this assembler directive. Anything starting with a dot, we call it an assembler directive. So whenever the assembler goes and see the dot, oh, I need to do something about this. There is directions that I need to follow. I need to include, oh, which kind of library? This library. And so after this, you have the dot global. Again, this is a directive declaring the label that you start your code with, which is the __ reset. It's a global. This way, definition, it's a global. So now you know where exactly your code starts. So the assemblers looks for this label. Whenever it sees the label, it knows that this is the start of the instructions. After that, we have the .pss. This, again, this is a assembler directive indicating that the following that should be placed in data memory, meaning that this is your variables. And you can see here that we defined for I and J and K spaces. Again, to define a space, you say dot, or you write down column followed by dot space. And then you see, or you write down the space length. So for a byte, you say we have 1 byte for I, 1 byte for J, and 1 byte for K. Again, just to repeat the same thing here, that the dot space assembly directive reserves space in bytes format, meaning each number you put here means that it's 1 byte. If you write down 2, it means 2 bytes, and so on. After this, now we explain the first piece of directives and the spaces for the variables. You have this part here. To highlight it more, you have the dot text directive, which is saying that what follows is the code. So you should look for the labels after that. Our first instruction must be labeled as __ reset, since you define it as the global label. So you can see that here, after that, you have columns, and then you have your statements. The beginning, you'll see these 3 statements, and you can see that you have SP, lim. We know that W0, W15, these are the working registers, and that's fine. But here we have SP something. The SP is the S standing for the stack. So here we have a stack pointer. We define the stack pointer. We initialize it. We initialize the stack limit registers as well. So this initialization, the assembler is responsible to do this generation. The compiler, once you compile, it adds the appropriate instructions to initialize the stack. After that, you will start having your code, starting with the this statement that we described before. Notice that the equal sign is an assembler directive that equates a label to a value, which is obvious. Now, after this piece of code, we have the code that we described earlier. This is the code. Same thing. Just know that we sometimes we use labels and comments to help us improve the clarity of the program. So now you know here the job of these 2 instructions is to assign 100 to I, this one to increment, these 2 is to assign I to J, and so on. So for each one of them here, it tells you exactly what follows it. And alongside or you have a comment for each line to describe exactly what it does. Now, you have to be careful. It's hard to over-comment an assembly language program if you want to be able to understand it later. So we should strive for at least a comment every other line. So don't comment too much. Also, don't skip commenting. You need to balance this to make your code clear. However, as we mentioned, we will write actually C code, and we will use the compiler to generate the assembly code for us. This is only helpful if you chose to write your assembly code yourself. Okay, well, let's continue. The last few labels and statements, instructions, we highlight them here. This is done label. You have done and column. go to done. So you go here, this is the label done, go to done, you go back again, go to done, go back again, and so on. This loops forever. At the end, the last statement you loop forever. So this is a label, that's the target. If I go to instruction, the labels are case sensitive, as you know. And we write down a comment here. We have so many comments that we described before. At the end of the code, so we have the assembler directive specifying that this is the end of your program. So it starts with .text and it finishes with .end. Now you might ask, why do we have an infinite loop at the end? This is a microcontroller. Our microcontroller doesn't have an operating system. So you need to exactly tell us what to do at the end of your code. So once you finish your code here, if you don't have this infinite loop, it will go out and the microcontroller will not do anything to your subsystem. To make sure that the microcontroller is still alive, you at the end, you should make the microcontroller stuck in an infinite loop. Okay. Now, again, just to remind you, there is a difference between clock cycle and instruction cycle. The clock signal used by the PIC24 microcontroller to control the instruction execution can be generated by many ways. One way is an off-chip oscillator or a crystal. And the other way is an internal RC oscillator. So basically, there is an external way and an internal way. And we will specify many types for each one of them, of these two, later when we talk about the oscillator. Anyway, now consider we have a clock that we generated already. Now for the PIC24, the maximum clock frequency is 80 megahertz. And don't forget that an instruction cycle is 2 clock cycles. For every instruction cycle, we need 2 clock cycles. That's in general. If you want to look at all details, you can go to the data sheet and you will see that some of the instruction, when you look at the ISA, and you look all the list of instructions that is supported by the PIC24, some of them have 1 or 2 instruction cycles. So there are instructions that needs only 1 instruction cycle. So just let me write it down so you understand the idea here. So we have many instructions. If we categorize them into 2, some instructions, they have 1 or they need 1 instruction cycle. Some of them, or the other type, let's say that this is instruction 1, and this is instruction type 2. The instruction type 1 needs 1 instruction cycle. Instruction type 2, they need 2 instruction cycles. This means that of this type, you need 2 clock cycles. What we say, this is what we said here, that every instruction cycle needs 2 clock cycles. If you need 2 instruction cycles, this means that you need 4 clock cycle for the next type. And as an example, from my memory, I think that for type 2, we have the go-to instruction. It needs 2 instruction cycle. For the first type, I think the increment and the decrement, they require only 1 instruction cycle. You can see all these details in the data sheets, it's tabulated for all the instructions. Basically, as a rule of thumb, if an instruction causes the program counter to change, like the go-to instruction, then that instruction takes 2 instruction cycles or 4 clock cycles. Now, this is some examples to understand the to see the relation between the clock cycle and the instruction cycles. An add instruction takes 1 instruction cycle. How long does it take to execute this instruction in PIC24 if the clock frequency is 80 megahertz? So you get the period by having the reciprocal of the frequency, 1 over the frequency equal to period. This means that it's going to be 12.5 nanosecond for an 80 megahertz PIC24 microcontroller. 1 add instruction at 80 megahertz takes 2 clock cycles. It's actually taking only 1 instruction cycle, which in turn requires 2 clock cycles. You multiply it by the period of 1 cycle, which is 12.5 nanosecond. And here you can get the time, which is basically what we can say here, that we need 25 nanosecond to execute the add instruction in PIC24. Now, if we say that how long does it take to execute this instruction, the same instruction, the add instruction, but here in a 3 gigahertz processor, which is like your PC. If 1 instruction cycle needs 1 clock cycle, as we explained here, if we say that they have the same clock cycle needs. So now we would say that the period is 1 over 3000 megahertz, which is 0.3 or a third of a nanosecond. 1 add instruction at 3 gigahertz takes 1 clock cycle now, which is basically 0.33 nanosecond. So here we change the specification for a PC. For the microcontroller, we say that 1 instruction cycle is equal to 2 clock cycles. For the PC, we said that we assume that 1 instruction cycle equals to 1 clock cycle. So you can execute 1 instruction for every clock cycle. If that's the case, then you can execute this instruction in a or a third of a nanosecond or 330 picosecond. What does that mean? It means that the current processor, your PC at home, could emulate the PIC24 faster than a PIC24 can execute in reality. So the emulation or the simulation using a PC of the microcontroller is much faster than the real thing. However, you can't put an expensive processor like Intel i9 in a toaster for a very simple system. What you do is you go to some company that sells microcontrollers, and you can buy a microcontroller for $5 or maybe even less than that, maybe $1 or less than $1 for a simple toaster. So that's the idea here. Now, if you are asked how long does your code takes to execute, beginning at the reset label, if we list the instructions and we count how many instruction cycles for each one of them, if you go to the table in the data sheet, you see that these instructions, none of them is go-to. They don't need to update the PC. So they have 1 instruction cycle for each instruction. We have 12 instructions. The total will be 12. So this code, it takes 12 instruction cycles which is 24 clock cycles. Now, going back to our simple program, we mentioned that we define the variables I, j, and k as 8-bit or 1 byte. What if you have a value that is bigger than 8 bits? We know that the range of 8 bits from 0 all the way to 255. Let's say you have a value that is more than 255 and you want to store it in the variable. What you will do is you will define it in 16-bit type. So you will have unsigned integer 16 and you have I and j and k. Notice here that the value is 100 and you can fit it in I, j, and k. The code will work fine for 8-bit. If you choose a value, for example, 2047, then an 8-bit won't fit it. You need more space. So the next jump from 8-bit is the 16-bit. This is 1 byte and this is 2 byte. And you will have the same code. If you see the difference between these two codes, the only difference is the change here. This is 8-bit and this is 16-bit. In C language, this is the only difference that you will see. If you compile it, the assembly that you will generate, this is for the MP test. If you use a byte, you can see that the spaces here are 1, 1, and 1. For the 16-bit version, the assembly code for it, you will see in the next slide. Notice that this is slide 32, just so you are aware of what's going on. In the next slide, we will show the 16-bit. This is the 8-bit. This is the 16-bit. This is the next slide. This is supposed to be 33. So here you have 2 bytes for each of the variables. Let me go back. This is the first, 32, slide number 32, slide 33. If you see the difference between those two, you can notice that the space is different, and also the dot B that was here previously are removed. So this B indicates that these instructions are for 8-bit registers or values, while this one, every one of these instructions is for 16-bit. To indicate this quickly, what we say, if it is an 8-bit operation or an 8-bit variable, we say that these instructions perform byte operation. While the other ones, for the other one, the instruction performs a word operation or a 16-bit operation. Now, again, we will try to calculate how long does the other code for the word to execute. Again, each instruction will have one instruction cycle with a total of 12 instructions, meaning you will have 12 instruction cycles, or you need 12 instruction cycles to calculate or to execute the code, which in turn need 24 clock cycles. Let's put them side by side. This is the code for the MP test underscore byte, and this is for the word version. You can see that both of them need the same number. So there is no difference in speed if you use an 8-bit variables or 16-bit variables for the PIC24. And the reason is the width of the bus is actually, or can accommodate 16-bit. The width of the data bus can accommodate 16 bits. So if you have less than that, which is 8-bit, you can also accommodate it as well. So whatever value you have, either 8-bit or 16 bits for the variables, you will end up with the same number of instruction cycles. To understand this better, let's have this discussion: the 16-bit operation versus the 8-bit operation. From this table, it depends on your microcontroller type. The PIC24 is actually 16-bit. We know that the data bus width is 16-bit. Now, if you look at the program version, whether it's 8-bit or 16-bit, it will have, or it will need 12 instruction cycles. However, if you have another version of the code that needs 32-bit variables, now we need 24 instruction cycles. And the reason is, again, because we have 16-bit bus width. If you have a 32-bit variable, you have to put this value in two phases. You will put the 16-bit high half word, and then the other 16-bit half word. So if this is the most and this is the least, you have 16-bit here and 16-bit here. Both of them together will be 32-bit. Your bus can accommodate only 16-bit, so you will send this one first in the bus, followed by this one. So you will take 2 instruction cycle for every instruction, and that's why you need, instead of 12, you need 24. In general, if you have 8-bit microcontroller and an 8-bit program, it will have, taking our previous example, you will need 12 instruction cycle. If it is 16 bits, 24, then you need to double it. If it is 32-bit, you double that. For a 16-bit, as we mentioned, 12 and 12 and 24. For a 32-bit, if your microcontroller data bus width is 32-bit, or the type of the microcontroller is 32, then you can accommodate whatever code you have. I just want to mention that it's not actually doubling exactly. You actually need more than 24 for some overheads of the hardware. You probably need more cycles. So maybe instead of 24, 26 or 25, similarly here and here. But for simplicity, we would say that we only double them. Now, this is, before we finish with this talk, this is just a revision for the units, because you can see that we talked about kilo, mega, giga, microsecond, nanosecond, even picosecond in the previous slide. So just remember that milliseconds is 10 to the power of -3, the micro 10 to the power of -6, the nano 10 to the power of -9. After the nano, you have pico, which is 10 to the power of -12. After the pico, we have femto, which is 10 to the power of -15. This is for the time. For the frequency, we have kilo, mega, and giga. You know that the kilo is 10 to the power of 3, and the mega is 10 to the power of 6, and the giga is 10 to the power of 9. If we talk about the frequency, we measure it in hertz. After the giga, we have others, which I think this is enough for the frequency. This is just an example for a frequency of 1.25 kilohertz. If you are asked what is the period, and I indicated that you need to show it in microsecond, then you would say that the period is 1 over f, which is basically 8. If you calculate it using your calculator, you'll probably have it as 8 times 10 to the power of -4. So now you could say that it's basically 8 to the times 10 to the power of 2 microsecond. This is in second. If you go to the microsecond, you have to move it 6 positions, since the micro 10 to the power of -6. And because of this, you would say that you have 800 microsecond. 800 microsecond, since 8 times 10 to the power of 2 is equal to 800. So just be careful when you write down. One common mistake is some people calculate and then you just write down 8 times 10 to the power of -4 and you don't specify the unit. That's wrong. I don't know, what do you mean? Do you mean second, microsecond, nanosecond? Also, some of them put the wrong unit. So if you put 8 times 10 to the power of -4 and then you put here by mistake millisecond, then that's totally different. That's you are shifting the whole calculation certain degrees. So you have to be careful of the unit. This marks the end of this talk. In the next lecture, we will talk about the C language. So it's will be closer to what you studied in the first year of the university, whether you studied C or Java or any other programming language. We will see. There is many similarities in the next lecture.